It is 11 o'clock. Let's get started. I told you that this week, everybody, let's get started. I told you this week I kind of wanted to just get into it with these review problems, and that is in fact the case. So if you have not yet scanned the attendance code, please do so. The only thing I wanted to mention, two things I wanted to mention before we jump into this. So for the bonus homework, which is due, that's the uploading proof you did the course eval. We haven't had a lot of students do it yet, which is not a big deal. It's not due till next Tuesday. But the big thing is that if you have done the course eval, but you haven't uploaded a screenshot that you did it, I don't know. So I know at least the last time I checked, there were 2 students that had done the course eval, but I don't know that you did it. So the only way that I know that you did it, I guess, is if everybody does it. But if you don't upload proof, you would be giving away free points. So make sure if you did it, upload points because they're free points. Again, you could say I'm a poopy head, that's fine, but I do want you to do it. I really do appreciate the feedback. Okay, the other thing I wanted, yes?
With that, I think it closes in 2 days.
Does it close in 2 days? The survey closes in 2 days, but but you could still upload proof until the final. So, but yeah, the course eval survey for Marshall, you are right. It does close Friday at midnight. So, but in case you do the survey but you forget to upload, you'd have time to do it. So, sound good? All right. The other thing I wanted to mention is that this was the problem that we did last time. Did you all get the code?
Thank you.
Gosh. No, I'm just kidding. All right. So the one other thing I wanted to mention is that this example that we did last time, if you check the class notebook, I did upload the solution because, again, my computer was being a little weird last time, so I just uploaded that here. And so that's there. I won't go too far into that, but everything that we put on the board last time is available there. Okay. Everybody ready to get to it? Let's get to it. Okay. So this is problem number 2. I've got 2 problems in this review that I just had a lot of fun putting together. This is one of them. So I have a 100 kilogram plate that is being subjected to a 300 Newton force right here and a 200 Newton edge moment applied on this far edge over here. And I would basically like to get the reactions. So I've got a reaction here, I've got 3 reactions here, and a tensile force in this cable. Okay, so we talked about that part last time. Let's draw that out. Okay, so I'm going to have some tensile force here, which I'm going to call it CZ. Okay, I'm calling it CZ because it's along the Z-axis. I'm going to have some reaction here, which I'll call AZ, and I'm going to have potentially 3 reactions here. I can do better than that. I'm going to scroll up a bit, make that a little easier. And I'm going to have a reaction right there, BX, BY, BZ. As for the directions of these reactions, notice that BX is along the x-axis, BY along the y, BZ along the z. I put them along the positive direction for each of these axes, okay? So I'm assuming that they're along the positive direction. So if BX were to be negative, it would just be going the other way, okay? Now, there are 3 reactions, A, B, and C. There are an additional 2 forces being applied to the system. So the 2 forces are F, the 300 Newton force, but what's the other force being applied to the system? And I'm not talking about this edge moment because that's not a force, that's a moment. What's the other force being applied to this system? The weight, exactly right. So the weight is going to be, I don't know, right there. Right? And how much force is that, by the way? That's a trick question because the answer is not 100. It is 100 times 9.81, right? Because give me 981 newtons. Does that sound good? Now, I am not saying that we are going to ignore this edge moment. Far from it. But it is not a force. It's a moment. Okay? So, I would like to list let me do this. Let's list all our force vectors. And by the way, I put a copy of the system down here. I'm going to drag that down a bit. Let's list all our force vectors, right? So we have force vector A, which is AZ times K. Force vector B, force vector C, which is right here. What about force vector F? How are you going to describe force vector F? Somebody tell me, how are we going to describe that in IJK notation? Negative 300K. It's K because it's along the Z-axis, and it's negative because it's going down. 100% right. Excuse me. What's the fifth force vector that I'm missing? The weight. And the weight is also going to be negative K, but it's going to be that. Okay. So far, so good? Okay, now, trust me for a little bit when I tell you that that moment vector is not a force. It's a moment vector, okay? We are going to use it, but it is not a force vector. The point I am making is that these are all the forces on the system, right? If these are all the forces on the system, when I sum these forces, what must they equal? So if that is the case, is there anything that you can do by observation? Is there anything you can tell me about any of these unknown components? You said something and you said something, and you were looking at the X, you were looking at the Y. You said that BX is 0 and BY is 0. You are 100% right. This has a K component. This is the only one with an I component. This is the only one with a J component. If I sum the forces in the X and Y direction, BX equals 0 and BY equals 0. So note, so I'm going to say that's all we got to deal with, okay? And I'll just say note, would you like me to give you a two-dimensional analogy to what I just did? Let me give you a two-dimensional analogy. Here, I'll put it here on, just put it right here. Let's say I have a beam with like a point load and a distributed load, how many reactions are here at the roller? How many reactions are here at the pin support? A vertical and a horizontal, right? But what is the horizontal reaction for this problem? Because there's nothing horizontal, right? That's the same thing that happened here, just in 3 dimensions. There were no applied forces in the x direction, no applied forces in the y direction. So yeah, there are forces there. I'm just showing that that force has a magnitude of 0. Does that make sense? Everybody okay with that? Okay. I just wanted that to be said, okay? We're still going to sum moments about B, okay? So, okay. So now what I want to do is I want to look at position vectors and I want to look at moments. Okay? So this is our problem, and we're going to sum moments about point B, just like we said we were. Okay, so we're summing moments about point B. Okay? So let's deal with each of the forces. Okay? So let's start off with A. Okay? So vector A is going to look like that, right? So if I'm drawing my R vector, I mean, how do we do R vectors? R go from the point of interest to the line of action of the force. So the R vector for this one just essentially is that, right? Oh, that's kind of, let me use a different color. That's the R vector, right? Just from here to here, right? Okay? And so we'll call this R vector 2A from B, right? So help me out. What is R 2A from B? How do we get to A from B? How do we do that? 2 meters in the y direction. Is it positive or negative?
Negative.
Because, yeah, this is positive y, we go this y. So the R vector is negative 2j, right? Does that make sense? To get from here to here, we don't go any in the x, any in the z, we just go y, and it's minus 2j. Okay? Sound good? And the reason that we're doing that, I'll put this here on the board, is because we're going to need to do a cross product like that to get the moment, right? Make sense? Okay? Now, there is a force right here, right? But do we need to write an R vector for it? No, because we're summing moments about that point. So what we would essentially be saying is that the moment from that reaction is going to equal that reaction, but it's going to be crossed with 0, right? And a vector crossed with 0 isn't going to be anything, right? Does that make sense? So we're not going to have to worry about that. So what about C? Okay, so we've got a C like that, and so the R vector is like that. So R to C from B. What is R to C from point B? How am I going to describe this vector? Negative 3I, right? Because it's negative 3 along the x-axis. Okay, and we're doing that because We're going to have to do that. So basically what I'm doing here is I'm writing a list of all the moments that we're going to have to compute. Okay? Does that make sense? All right. Am I going to need any more R vectors? How many more am I going to need? 2. Because I'm going to need an R vector here. So what is the R vector to F from B? So how far do we go in the X direction? -1.5, and then along the Y, -2. Okay? Is everybody okay with that? I want to make sure that identifying these vectors is like, okay, comfortable. Everybody good with this? Okay? And then there's the weight, right? Remember, the weight is sort of like right here. So the vector is to the weight from B. Okay? Which is going to be what?
J.
Is it 1? Well, hold on.
Is it -1.5, -1?
Yeah, because it's still going to be to the middle of the plate this way. Like along the x-axis, so the plate's 3 meters wide. It's still going to be 1.5 this way. But 1 here, right? So really the only difference is minus 1.5 I minus 1J. Okay, does that make sense? Is everybody okay with that? So, and again, what we're going to have is MF MW. Okay. Does that make sense? So, all right, here's my point. Okay, so there's the R vectors. Let's see if we can write down our moments. So let me write down what I've got here on the board so far. So, and I'm going to skip the B. Okay, so I have 4 cross products that I'm going to need to compute, okay? But are there 4 moments? There's 5. When I sum moments, I have to sum 5 moments. Which moment am I forgetting? The edge moment. So what that means is I need to describe this moment as a vector, right? How do I do that? Okay. Okay. And the answer is the right-hand rule. Do y'all remember the right-hand rule? So what happens? Your thumb goes along the axis of rotation, right? And your fingers curl in the direction of positive moment, right? So, oh goodness. Oh, you go away. Don't laugh. So, I said don't laugh. I'm kidding. All right, so my thumb is going along the y-axis. Why is it going along the y-axis? Because the moments are rotating about the y-axis, right? Now, if my thumb goes in the y-axis, are these moments rotating in the direction of my fingers or opposite my fingers? Opposite. So I would then say that this moment can be treated as minus 200J. And the units would be Newton meters, right? Like a foot-pound just in metric, okay? Does that make sense? So when we sum moments, we're just going to sum up all the cross products, but make sure we add a negative 200 on the y term. That's it, okay? Like I said, this edge moment is a lot simpler than you would think, okay? Everybody good? All right, so let's see what happens. One of the other things that I'm hoping that is clear is, well, I'm getting ahead of myself. I'll talk about that later. Okay. All right. Let's start doing some cross products, okay? So let's start doing these. What was this first one, by the way? What was RAB? Negative 2J. So this is going to be, and then this one is just that, right? Okay. So let's see. Let's see if we can reason our way through this. So if we do cofactor expansion, we're going to have an I term times what? Because it's going to be like this minus 0, right? Okay. What about the J term? What's the J term going to be? 0 and 0, right? What about the K term? 0 and 0. So that's it, right? That's the cross product right there. Just minus 2AZI. Is that okay? Did I do that too fast? Okay. Let's try MC. Okay, what was RC? Negative 3I, so minus 300. Okay. All right, so let's see. So is there an I term? Yeah, 0 and 0. K term. 0 and 0. So J, so what do we have for J? We're going to have J, we're going to have negative 3Z, right? Negative 3CZ, right? So that times that. But remember, how does the cross product work, right? The cross product goes like this. We have I times a determinant minus J times a determinant plus K times a determinant. Okay, this and this go to 0, right? So we're going to have minus J times that, right? And then, so we're going to have minus J times minus 3CZ, right? So this is going to be plus 3CZJ. Is everybody okay with that? Like the signs? I would say that's the hardest part. And so, again, bless you. Again, I mentioned, don't skip steps if you're feeling unsure. And this is one of those things where, like, the problem's easy, but getting the pluses and minuses, you don't want that to trip you up on the exam. Okay? So, MF. Okay, so now we're actually going to start having some numbers, right? Because this is IJK. So now we've got some numbers. Okay, so let's start off with the I term. So knock out the row and column here. We get negative 600. Or wait, no, positive 600. Wait, did I get my sons? Oh, no, I forgot a negative here. 600I. Okay, let's see if we can do this J term. Okay, so J. Okay, we got a lot of negatives here. So first off, let's just do this. Let's just do the multiplication. So cross out J. We get 450, right? But then the whole J term itself is negative. So it's a minus 450J. Okay. And then for the W, (1.5 minus 1), or negative 1.5 minus 1. All right, so what do we got here? So cross out, we get 981. And then for the J, it's another one of those like triple negatives because we got a negative times a negative, but then the whole term was negative. And then it's 1.5 times 981, which I can go ahead and tell you that. That ends up being 1471.5. So how are we doing? Is that good? Okay. All right. Any questions? All right. So now what we need to do, so whenever we do one of these problems, we want to sum moments first, essentially. So let's sum moments and let's see what we get. All right, so what do we got? We've got MA. We've got that. All right, that's MC. MF. That's MF. MW. And did I forget one? The edge moment, right? There we go. So, I don't know about you, but I mean, we can handle each one independently, right? Because we can sum this column to get AZ, sum this column to get CZ, right? I'm going to do this column first. So if I sum moments about the x-axis, so summing moments about the x-axis, so what do I got? I've got, move the 2 onto the other side, get 2AZ equals, so 600, 981, 1581. AZ is going to be that over 2, 790.5. And that's newtons, right? And then for the summing of the moments about the y-axis, you kind of see what I'm doing here, right? Just summing up all these terms. So this is going to be 3CZ is, was that 21.5? And then this one has got a repeating decimal. This is 707.17 newtons. It's like 0.1666666 repeating. So what do we have left to solve for? What's left? BZ, right? Because we got BX is 0 and BY is 0, right? So how do we do that? We sum the forces. And we're basically just summing forces about the z-axis at this point because we already did sum of forces about the x and y. We did that at the very beginning of the problem. And so what do we got? Well, we've got AZ plus BZ plus CZ minus 300 minus 981 equals 0, right? Because there were only 5 forces on the whole problem. And we now know what AZ and CZ are. So BZ is just that. And sum that up. And we get that BZ is, it actually is negative. And there's our answers. That was a long problem, but what do we think? Was that a good problem? Good review, right? It's been a while since we've done stuff like that, hasn't it? Okay. Does anybody have any questions on this? Everybody good? Okay. Are we ready to go ahead and go to the next problem? Okay. Where's my... Oh. So the thing about centroid problems is I'm hoping this problem is relatively quick. What I'm not going to do is go through like every single individual calculation by hand. The big thing is just being organized, okay? A couple things worth mentioning. We've been told that every hole is 1 inch in diameter, okay? So, all right. So, let's see. Oh, yeah, okay. The area of a hole then is going to be pi over 4. Is that okay? Everybody okay with that? All right. So I think I have a little typo in my hand calc, so we'll just sort of play that by ear. Okay. All right. So what I'm going to do for my shape discretization is I'm just going to split it up like this. Okay. So I'm just going to say this and this. I'm just going to slice it like that. So we're going to call this shape 1. I can do better than that. I'm going to call this shape 2 and shape 3. We'll call that hole 4. Call that hole 5. Okay? Does that make sense? And I think I'm probably going to call an audible and not do the moment of inertia calculation in here. I might put that in the notebook. But because I think the centroid calculation is far more important. Okay. All right. So we're going to calculate the coordinates of the centroid both along the x and y axis. Okay. And let me see if I can do that. Let's see if I can do it like this. Okay. So we're going to do a sum here. So the first thing we're going to do is list the areas. Okay. So what's the area of shape 1? 20. What's the area of shape 2? 8 times 4, and this is 8, right? So 24 and 8. Now what about each of the holes? Each of the holes are pi over 4, right? Pi d squared over 4. So I'm just going to write those as negative pi over 4. So the total area then is going to be 32 minus pi over 2. Is that fair? Is that fair? Okay. Let's do the x-axis. Then we'll do the y. So again, now here's something that I noticed on the exam, and I want to make sure that we're all crystal clear about this. These x distances are all measured from the same spot. They're measured from there, okay? So a lot of you would, like on the exam, would take like shape 3 and say x is 2. That's wrong, okay? For shape 3, x is not 2. What is x for shape 3? 7, because it's 5 plus that, okay? So don't forget that, okay? So what goes, let's see if we can figure this out. What is the x value for shape 1 going to be? 5. What about this one? 5 and a quarter? 5.25? What about shape 3? We said that's 7. What about shape 4? 1. And what about shape 5? What's it going to be for shape 5? 8. Right? Does everybody see that? So it should be 5, 5.25, 718. Is everybody okay with that? Okay. So for the y-axis, the same story. So y for shape 1 is not 1, okay? Is it 9? See, so from here, 2, 8, and then 1, so it's 11, right? Is everybody okay with that? This is 11. What about for shape 2? What is it going to be? 6. Right? Because you're going to go up 2, then half of 8. So up 2 and then up 4. 6. What about for shape 3? 1. Okay. What about shape 4? 11. What about shape 5? 1. Okay, does that make sense? Okay. So XA is going to be 20 times 5, 100. 4 times 5 1/4. So 4 times 5 is 20. 4 times 1/4 is 1. So 21. Is that fair? 8 times 7, that's 56. And then pi times 11, so 11 pi over 4. Oh, sorry, I'm thinking of the y's. Sorry, whoops. Right, so that's pi over 4, and then 8 pi over 4, or 2 pi, what have you. So this is going to be, what is that, 177 minus 9 pi over 4. Did I do that right? Since I don't have my calculator on me. Is that fair? Yeah. Okay, and then for YA, $20 times 11, 220. 4 times 6, 20. 8 times 1, 8. And then this is the minus 11 pi over 4 minus pi over 4. So this is going to be like, what is that? Wait, did I get one wrong? Did I do that right? I think 24. Yeah, 24. I was like, something didn't look right. Is that 252 minus 3 pi? How'd I do? So X bar and then Y bar is okay. And somebody help me out. What do I have for each of these? What about X bar? We'll say 3 decimal places just to see that we're all getting the same thing. Yeah. 5.584. Do I have a second? Okay. All right. What about Y bar? $6.010. Do I have a second? I had a typo on mine, so I don't have this answer. So you're getting somebody shaking their head. What'd you get?
I got 7.97.
7.9.
7.2 actually.
7.972. Did you? Okay. Okay. Okay, let's take a step back. Let's see, did this make sense? I would say the biggest thing to make sure that you're comfortable with are these two columns right here, X and Y. Those were singularly the biggest source of mistakes on the exam. All of the distances need to be measured from this point, because what is this? These are the coordinates of the centroid from here, right? That's the whole point. So I said point a lot the last couple sentences. All right, make sense? All right. Any questions? Because I want to show you a couple things before we get back on Friday, okay? Okay, let me show you a couple things about the next two problems, okay? Okay, I thought it prudent to have a truss. So we're going to do this truss together, okay? I'm going to tell you with this truss that one of the members in this truss is going to have a very interesting answer. And it is this member right here, okay? We'll get to that next time. Unless you want to go ahead and try it on your own, I'm not going to stop you. But if you try this on your own and you want to come back, what I'll tell you is you're going to get something unique on this member, member AB. And what I will say is member AB, as you're doing the problem, may confuse you, but go with it. That's what I'll tell you. Go with it, because it's probably right, okay? All right?
If it makes sense, we're wrong.
I didn't say that. I'm just saying it's a unique response. Okay, the other thing I want to mention is about problem 5. So let me explain what's going on with problem 5, because this note here is very, very important. Okay, so when we did beam analyses, we would use this symbol as like a roller, right? And we would use a triangle as a pin support. And we would say that like just on first glance, this looks like a fixed support, right? But that's not what's going on here, okay? So what's happening here on this problem is we have a beam, okay? We have a beam. Let's say this water bottle here is the beam, okay? And the water bottle is the beam. It's got a series of loads on it. And then there's this 40 kilonewton load right here. And what it's doing is it's pushing the beam against the wall, okay? And so we're putting load on the beam. And so what's happening is equilibrium is being maintained through friction right here, okay? So what I am proposing is for point D, okay, there are going to be two reactions. The first reaction is going to be that if I press this against the wall is pushing back, right? Okay? So that's where the first reaction is coming from. Where is the second reaction coming from? Like if I stack this on top of the water bottle, why is the water bottle not sliding? Okay? Well, it's not sliding for two reasons. One, I'm pressing it in place, but why is it not sliding? Friction. So I propose that this point is going to have a horizontal reaction and a vertical reaction, but it's not going to have a moment, okay? It's not going to have a moment because this is not a fixed support, okay? This is a friction surface, okay? And so what we're going to try and figure out is what is the maximum amount of load that we could put on the beam before it starts to slide? And then what is the shear and moment diagram under those loads? And then if we really wanted to get fancy with this problem, what I could do is I could say, okay, the beam can hold up this much load before it fails. What's going to happen first? Is the beam going to slide or is the beam going to snap? You know, we could have some fun with it. But we'll talk about that on Friday. Does that sound good? All right, has the review been going good so far? Good. All right, I'm going to pull up the code one more time. That's all I got, everybody. I will see you all on Friday.